Welcome to the electricity unit. We're studying two broad forms of electricity, static and current electricity. What you should be able to do by the end of this unit is relate the structure of the atom to electricity, explain the characteristic voltages and current involved with both kind, and why the name static and current were chosen and how that makes your discussing it easier. I want you to be able to make successful analogies to explain the difference between current and voltage and identify real-world examples of their use. The two terms are fairly self-explanatory. Static means you're sitting still. Current implies flow, like a river. Static electricity will build up on surfaces and it will shock you, but the shock is brief. It's over in an instant. This lightning bolt is over in an instant. Current electricity, on the other hand, continues to flow. So when you turn a light bulb on, the electrons flow down the wire in a continuous fashion until you cut the circuit. If lightning was a current phenomenon, then the lightning bolt would strike and it would continue to burn at that spot for days and weeks on end. Instead, it's just a single big explosion. So in a sense, a static shock is like someone throwing a water balloon at you. It bursts and it's over. Where a current example would be turning a fire hose on a person. It just doesn't shut off. Current electricity typically goes in a circuit. So we have some flow that will start at some origin, say a battery. It might flow through a meter that tells you how much juice is still left in your battery. Then it goes through some device that drains it of energy, and then it goes back to be pumped again. So it's a closed circuit, kind of like the lazy river in Canada's Wonderland. The first confirmed use of electricity was by Alessandro Volta in the 1600s. He built this battery pile. And it was basically, you could have taken, in the old days, we'd use pennies and nickels. Now you're going to have to use a nickel and a loonie or a nickel and a quarter, and you stack them and you put pieces of paper in between so they don't touch, soak it in lemon juice, and you'll have a battery strong enough that if you put those electrodes in your mouth, you'd feel a tingle of the electricity. In addition to batteries, we can make current electricity in a lot of other ways. We can boil water, whether it's coal, oil, or nuclear energy, and we use steam to drive a turbine, something similar to a jet engine. We can use falling water to spin that turbine, and in all cases, the turbine's connected to a generator. There are non-mechanical means of generating electricity, solar and nuclear power packs that have no moving parts whatsoever. These nuclear power packs are favored for deep space probes because they will produce energy for essentially eternity and they can't break down. But they're hideously expensive and staggeringly dangerous, so they're not something you're ever going to get in your house. Both forms of electricity originate from the atom. We have the electron and the proton inside. The movement of electrical energy only involves the electrons, that they will leap from one atom to another, these valence electrons. And this was not known until 1897. Prior to that, they just knew there were charges. They just had no idea how they were related to the atoms themselves, that the atoms were in fact made out of opposite charges. Now, one of the characteristics of electricity is voltage. Everyone here knows about 9-volt batteries, 1.5-volt batteries, 120-volt household electricity. So the voltage is the energy the electrons have. Except we're not talking about one electron. We're talking about a bundle of them. So this child here is putting energy into this marble they're about to let fly with. So that would be like the voltage on a battery. The higher the voltage, the bigger the stretch, and you're going to fire the electron with a lot more energy. In imperial measure, the energy would be measured in calories. In metric, it's joules. So in a day, you eat about 10 million joules of energy. A single volt is putting 1 joule, not into one electron, because that would be an incredible amount of energy. You're putting 1 joule in a cup full of electrons. This cup of electrons has a name. We don't worry about it right now. So this would be like saying, oh, I'm going to put 1 joule of fruit juice or 1 calorie of fruit juice into a cup of water. So it's a bundle. If we wanted to show this person having the equivalent of a cup of electrons, they would have a bag at the end, like a hacky sack filled with particles. And then you could say, oh, they put all this energy into the bag of particles. So 1 volt is 1 joule of energy put into a bundle of electrons called a coulomb. The characteristics of current electricity is that it flows. We already talked about rates before, liters per minute, dollars per hour. Okay, it's a flow rate. This is a total. This is a flow rate. The flow rate in electricity is called an amp. And you go, what is an amp? It is basically the equivalent of liters per second. So if you have a 5 amp circuit, it is dumping 5 cups of electrons every single second. A 10 amp circuit is dumping 10 cups of electrons every second. So it's not a total. A lot of people think amps are like, how many amps are in this battery? No. It's not amps. It's cups. These are the amps. It's a flow rate. More on that later. The key difference between the two is static electricity sits still and often has extremely high voltages, like 50,000 volts. But there is no flow or current, no great number of electrons. So the total energy is usually weak. So when you get shocked with your sweater at 50,000 volts, it would be like a person launching a grain of sand at you out of an air compressor gun. It's going to hurt like hell when it hits you, but it's such a tiny amount, it's not going to harm you. If you went to a car wash and you turn the washing hose onto your own skin, it's going to peel skin off, but it won't kill you. But current electricity, the flow is what's enormous. It comes out very sluggish, but like Niagara Falls, the total amount of it coming per second is so huge it would wash you away. So static electricity would be like putting your hand in the way of a jet spray for a car. It will sting, nothing more. Current would be like trying to walk under Niagara Falls. The flow is so ginormous, you would be killed. So I've got that right here. Right? Current, think of a tsunami. Static, think of a car wash. Short, quick bursts.